All right, guys, your attention. This is the wrong whiteboard. So let me make sure everybody sees this. Okay, so you had trouble with numbers 5 and 6. Okay, so that's not very good. Okay, so it says a bag contains 10 counters, of which this is some page. Of which six are red and 4 are green. A counter is chosen at random. Its color is noted and it's replaced in the bag. So here's how we do it. We pick a counter. We say, okay, it's color whatever. And we put it back in the bag. Okay. A second counter is then chosen at random. Find the probabilities that both counters are red. So they're asking us for the probability that both counters are red. So what is it? Is this, huh? Okay, so, okay, what are the chances? Okay, just think about this for a second. I want you to think about it. All right. And unfortunately, this requires a little bit of thinking. You know, I'm not even going to draw it. Should I draw it? Just do a square. Oh, yeah, that works. Okay. Okay. Like, you see how comfortable I am right now? You know what? I give you permission to adjust the board as you see fit. How about that? But it would require you to get out of your desk. Like, you do this. Look, let me show you how you do it. Tell me, go like this. Tell me when. Oh, like that. All right, good. All right, so let's think about the question. The problem with this question is it requires more tools than was covered in the last section. The best way to do it is to do it with, realize that this is an and, not an or situation. So they're basically saying, what's the probability that you're going to get red and red? And you don't know now enough to do that. See, what they would have wanted you to do is they would have said, okay, a bag contains 10 counters of which 6 are red and 4 are green. The counter is chosen at random, its color is noted, and it's replaced in the bag. A second counter is then replaced. A second counter is then chosen at random. Find the probabilities that both are red. So here's what you do. You go, look, you can get red on the first one and red on the second one, right? Let's just call it RR, just to keep it simple. Or you can get red and you get a green. Wow, that's really bad. Those R's don't look like R's. So you get red and red, or you can get red and green, or maybe you can get green and red, or green and green. Those are the 4 possibilities that can happen. But here's our problem. On the first draw, how many ways can you get red? 6. And on the second draw, how many ways can you get red? 6 more, because there's 6 still. Give me 1 second. My wife is apparently calling me. So maybe it's because it's the doctor, and I can't get my. Yes. Dime. Abrí 20. Coño, pero a ver. Abrí, eso, mayo, junio, julio, agosto, septiembre, octubre, noviembre, diciembre. El bebito nace en enero. Después. Ok. Está bien. Okay. Está bien. ¿Abril qué? Abril 20. Ok, so va a ser abril 20. So hay que esperar un mes entero. ¿Y cuándo tú empiezas las inyecciones? ¿Progesterona o estrogena? Está bien, te llamo para te estoy enseñando, ¿ok? Bye. Okay, so um so here's what happens. What you got to realize is that there are going to be 6 ways on the first draw and 6 ways on the second draw to get red and red. So there's going to be 36 ways that you get red and red. All right. So now, what about how many ways you get red on the first draw? It'd be how many ways? 6 ways. How many ways you can get green? 4. That's 24. How about green and red? How many ways can you get that? How many ways can you get green? How many ways can you get red? So that's 24 ways. How about green and green? There's 16 ways. Okay. Now, how many total results are there possible? Well, it's not that hard to figure out. How many total ways are there? Well, you could add that. How are you doing, sir? What's up?
Can I stay?
Yeah. Do you get attendance? Okay, okay. Okay, so how many ways could I draw those two? So how many ways can I draw the first one? How many ways, how many possible counters can I draw? Assuming, how many counters do I have? 10. And how many ways so total would be 10 times 10. Could you guys check if 36 plus 24 plus 24 plus 16 adds up to 100? So yes, there's a total of 100 ways. And so what's the probability to get red and red? It's going to be 36 out of 100. How about both counters green? 16 out of 100. How about just one red? Well, that's going to be 48 out of 100, right? You could reduce. Just one red is going to be red, green, or green, red. Where? Total. It's copyrighted, whatever it is. It's trademarked. The last counter red, well, that's going to be 24 out of 100. And the second counter is red. That's 24 out of 100. At least one counter. Sorry, at least. So at least one counter is red. It's 36 plus 24 plus 24. So that's 48 plus 36. 48 plus 36 divided by 100. And this is 14. Carry the 1. 84 over 100. The second counter red is 24 out of 100. And you're done. But you had to know that. You had to know that that's the way. And unfortunately, it is self-explanatory. That's why we need to practice. It was a lot easier, actually. This was like the problem that was challenging. So now let's take a look at 6. So, April 20 is the day they're going to put the embryo. So, yeah, but that means the baby's going to be born in January, which means I don't get a tax deduction for this year. I had to have the baby born in December, so I can take a tax deduction when I do my taxes for the year 2020. No, we could do it before, but the doctor that's treating my wife that's with us is going to be only available in April, not in March.
Yeah, that's not fair to the baby.
All right, it's a January baby it is. Okay. Huh? Well, I guess so. I would have preferred because 13, 16, 19, 22, all babies 3 years apart. But now it's going to be 4. And to remember birthdays that way, you know. All right. Draw a bar chart to illustrate the probability of the various total scores when 2 fair dice are drawn simultaneously. I should go over this one with you. And because it's a classical problem, and if you understand it, it'd be nice. But again, you guys have to go home and dream about this. Yeah. And they're fair, meaning that it's not weighted on one side to get, you know, it's supposed to have, I guess, a center of gravity in the center. Okay. So let's think about it. So the total scores. So do you remember last class I did this with you guys? 1, 1, 1, 2. Remember that? 1, 3, 1, 4, 1, 5, 1, 6. And 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. And 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. And 5, 1, and 5, 2, and 5, 3, and 5, 4, and 5, 5, and 5, 6. And 6, 1, and 6, 2, and 6, 3, and 6, 4, and 6, 5, and 6, 6. Agreed? So we do the scores. It looks like this. The scores are 2, 3, 4, 5, 6, 7. And then we have 3, 4, 5, 6, 7, 8. And then we kind of make a separation. So remember this here's for number 5, and this here's for number 6. None of your teachers are using this. Why not? Get it. Don't buy an iPad. What happened? They are. It's great. But the thing is, man, this is better, but it doesn't link up with my phone, which is Apple. Which is kind of like, why can't Apple just make an app that works on Windows? But they don't want to. Which is their, you know. Yeah, I know, but I know, whatever. Okay. You could, yes, but. Okay, so now we're going to make a bar chart of this. But however, what are the different scores you could get? What are the different scores you can get? You can get a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, or a 10. And now, unfortunately, say again? Or 11 and 12. I'm missing 11 and 12. Because these are the results of the scores. Yeah, I know. I'm being dumb. And so now we count. How many 2s do we have? How many 2s do we have? 1. How many 12s do we have? How many 3s do we have? How many 11s do we have? So this here is a frequency distribution. If we add up all our frequencies, girls, you're yapping the whole class. I mean, you're hardly audible, but it would be nice if you learned this stuff. What did you lose? Okay. Well, just restart the game. You should be able to find it. All right. So now we do well, they want us to make, the question was draw a bar chart to illustrate the probability. So they want probabilities. So I got to convert this frequency distribution into and it's a discrete probability distribution, right? We're going to convert it to a probability distribution. Do you remember how to do it? 1 divided by 36. 2 divided by 3 divided by, go ahead, 4. Oh, this is ACE. Yep. 5 divided by 36. 6 divided by 36. Oops. 5 divided by 36. Almost messed up. 4 divided by 36. 3 divided by 36. 2 divided by 36. 1 divided by 36. And then you get decimals for this. It should be decimals. 1 divided by 36 is 0.03. I'm going to go ahead and round to two decimal places. Not the best practice, but whatever. I'm in a hurry. 2 divided by 36. That's 0.06. 3 divided by 30. 3 divided by 36. 0.08. 4 divided by 36. 0.11. 5, oops. 5 divided by 36. 0.14. Oops. 6 divided by 36. That's 0.17. And then 0.14, 0.11, 0.08, 0.06, 0.03. And what should this all add up to? It should add up to 1. I don't know if it does. I don't feel like doing it, but I'll do it, sort of. So, okay, I'll wait for you then. Now, sometimes it doesn't add up to exactly 1, but it'll be 0.99 or 1.01. It depends how you round it and how many decimal places there were, you know. So, yeah, the problems, they're not exactly challenging, but if you don't know where to start, then it's a problem. You can't do it. 1.01, I'm fine with that. But are we done with the question? Did we create our bar chart? The answer is no. So let's go ahead and do it. So here we have this, and I guess you could, your x's are going to be here on this axis. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. As far as a scale is concerned, I think a good scale here, I'm gonna go by 0.02s. 0.02, 0.04, 0.06, 0.08, 0.10. Right now, you know what I'm thinking in my mind? I'm thinking of the show Loki and when they're gonna come out with the next season. You hated it? I'm sorry to hear. They're not?
I don't think they're gonna come out with a new. I think it's just going to be the new. So they gonna be the new multiverse of madness. It's probably gonna be that.
How about the one with the girl? No, WandaVision also.
No, I'm pretty sure. No, WandaVision not going in the multiverse. All of those are going to be the multiverse. None of them are going to have another season. That was literally the whole point. Disney wants you to pay for the subscription to watch the show and then watch the movie.
These people are evil. I would have loved to see like, oh my gosh, okay.
Like now I have to watch all of the shows because they're all the same movie. No, I didn't watch the shows. No, it didn't. And same with what if.
Hey guys, what do you notice about this distribution?
It's linear. Oh no, but it's symmetrical.
It feels like it's gonna be a bell shape that we're gonna learn about later on. Maybe it's normal. Maybe there's some, you know, and that's how it comes out. By the way, this is a very important shape. Okay. Empirical. There you go. Empirical. Huh? It's a normal distribution, bell shape. Okay, so are all bell-shaped distributions normal? No. However, all normals must be bell-shaped. Okay, now, all right, I did the two problems for the homework. Could you potentially see how you could actually do this on your own? It's not too bad, I think.
I have a question. Like, where are these numbers from?
Okay, when I roll a die, one die, it can come out 1, 2, 3, 4, 5, 6, 7. When I roll a second one, it could be 1, 2, 3, 4, 5, 6, 7. 6, sorry. So it could be 1, 1, or maybe a 1, 2. When you roll two dice, those are the results you get. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, right? And then the other one is the result of 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. That's the result of the sum of those two dice.
Okay.
Does that make sense? All right, so now I want to go ahead and continue with this. And so we're going to go today. I'm going to kind of review what we did last class, sort of, kind of, maybe. I'll wait because I see some people still writing. Or you're going to take a picture. See, he's using an iPad. I'm using a Surface. Now, that is convenient. It is convenient because everything stays together. But every time I have to save something on the iPad, it's a mission.
Files out.
No, bro, it's easier here.
I have folders now.
Yeah, I think you don't have to go into Google Drive. You don't have to
Okay.
find the file and then go to your Gmail and save it. It's all there.
I'll give it a shot, but the thing is, man, I have an iPad Air 4, whatever that one is. And it just, I don't, this makes my life, like when I try to run this, that what I'm doing right now on iPad in a class, I want to go, it's just bad.
So I'm sure like it's harder, like sharing stuff, but at least like just to use it regular.
But I'm, okay, Apple fan girl.
Not a fan, girl. I don't have an iPhone, but it's just easier.
Oh, yeah?
It's easier.
I don't,
That's also true. Airdropping files.
only if there's other Apple people around you.
Well, I'm trying to airdrop a picture from my computer to my phone.
Listen, I know I haven't, I have the Apple products too, but for the class, I have so much trouble. All right, guys, so let's continue. So now I'm going to kind of review what we did last class and go extend into what we're doing today. And then, of course, that's going to generate a group of problems. Be careful. A group of problems that you're not going to like. Well, hopefully you can.
Do we ever like?
No. Okay, so last class we said the following. We said, hey, listen, the probability, I'll do this in purple. So the probability of an event A or B must equal the probability of A plus the probability of B minus the probability of A and B. Now, if events A and B are mutually exclusive, then the probability of A or B must equal the probability of A plus the probability of B. As a consequence, that's called our addition rule. Addition rule. Okay, now, when we're dealing with probabilities, we have two basic rules. The probability of X or an event must be between 1 and 0 inclusive. If you add them all up, it has to equal to 1. Now, there's an extension here. The probability of A or B or C or dot, dot, dot. It's just going to be, just add them up. As long as they're mutually exclusive, the probability of A plus the probability of B plus the probability of C. You just keep on adding them over and over again. Now, another important thing that's happening here is you got to remember what mutually exclusive means. Mutually exclusive means that A and B cannot happen at the same time. So that means that the probability of A and B is 0 for mutually exclusive events. That's it. That's what we did last class, technically. So we're going to go into what we call the multiplication rule. And I'm just going to state it out what it is. If you have the probability of A and B, it must be equal to the probability of A times the probability of B given A. And I'm going to make a note here that this is read B given A has happened. This is called a conditional probability. Okay. So what is a conditional probability? Now I'm going to talk about this very simply from the cards perspective. All right. So let's just focus on conditional. What's a conditional probability? This room is cold, man. All right, so it was cold right now. Let me open those windows up. I don't know. Is there any way to redirect the sun in here? A mirror? You do the mirror and then one of the witches in the class starts melting. Who's a witch in the class? Do witches melt with sun?
No, it's water.
With water. Whatever. Vampire. Okay, vampire. Who's a vampire? Nobody hears. Okay. Yes, thank you. This looks like a head of a robot.
I was going to say when you were doing
Let me not.
Okay, so
And then you put the words last class like in the middle, so it looked like a.
all right, so focus on conditional probability. So let's talk about what conditional probability means. Okay, a conditional probability, I mean, it's always there. The question is the event independent or not independent? But look, let's say we're picking a card from a standard deck of cards. How many cards are in a standard deck of cards? All right, I'm gonna say, what's the probability you get a queen given the first card was a king? So let's say you pick the card, it's a king, right? And you put it back in. So this is important. So we're gonna say with, and we say with replacement, with replacement. So let's go over the experiment again. I go, okay, what's the probability of queen given king has happened? But you put the king back in. So what's the probability of getting a queen? 4 out of 52. Okay. Because how many queens do we have in a stack of cards? Okay, so this is important. I go over it. In a stack of cards, there are 4 of everything. So you have 4 2s. Okay, so I don't know if I want to go through this trouble right now. Yeah, I'll do it because I'm pretending to be a teacher. So you have a 2, a 3. Wait, let me do this in a different color. Okay, let's do the color, rainbow colors. You have a 2, you have a 3, you have a 4, you have a 5, you have a 6, you have a 7, you have an 8, you have a 9, a 10, you have a J, Q, K, and A. Now, you can either have a 2 of hearts let me make it thinner. I gotta change the thickness of that pencil. Here we go. Let's try this one. You have a 2 of hearts. You have a 2 of diamonds. Notice I did them in red on purpose. Okay. And you have a 2 of spades and you have a 2 of clubs. So you either have red cards or you have black cards. Each one of these cards exists in those suits. All right. Now that means we have a queen of hearts, a queen of diamonds, a queen of spades, and a queen of clubs. Simple, right? So now the next question is, what's the probability of queen given king without replacement? And what does that mean? Exactly. What this means is I pick the king first. Okay, great. And I keep it. And then I'm asked, what's the probability to get a queen given king has happened? In this case, we say it's 4 out of 51. Now, both of them are conditional probabilities. Our condition on both of these was king has happened. However, in this case, we say events. So let me see. I mean, I really had this. You know what? In this case, we say events, king and queen are independent. That means king did not have any effect on the probability of queen. Because here's what happens. Here's what happens. If you analyze it carefully, you know what? Let me not be so sloppy. Here's what I'm going to do. So it stays on your notes. Let me not be lazy. I'm going to go ahead and lasso this here. I'm going to drag it to the side. Bro, this is like magic. Are you sure you guys don't want to convince your teacher to use this? I'll just hype it up. No, man, that's too much work. No. All right, look. So this one we would say that king and queen are independent. While here we would say king and queen all right, so notice that in the case of with replacement, king and queen are independent. That means that king did not have an effect on the probability of queen. Why? Because if we analyze the probability of queen by itself, it's what? 4 out of 52. And since the probability of queen given king is the same, 4 out of 52, king did not have an effect on the probability of queen. Therefore, we say when it's with replacement, we say the events replacement, the events are independent. Independent. Now, in the other case, yes.
So the information is that you put the card back in the deck without.
Yes, because in one case, you're resetting the stack. In the first case where you're putting the card back, you're resetting all the probabilities to the original. But in the other one, you have a change. So in this other one, the probability of queen by itself is 4 out of 52. And the probability of queen given king is 4 out of 51. Therefore, we can make, this is without replacement. Josue, why has your attitude changed this last 9 weeks? Any reason? Just yourself? What made you feel like you should change your attitude?
That's the last math or whatever. I got into
Okay. 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 I see what you're saying. All right. Fair enough. That makes sense. All right. So we say this. If the probability of an event A given B equals the probability of A, or the probability of B given A equals the probability of B, then events A and B are independent. Yes. Else the events would be dependent. So now we establish when events are missing like a bunch of letters here. When events are independent or dependent. Fair enough? Make sense? Yes, sir. Yeah, like this. Now there's other ways to explain this, and if you go through the book's explanation, it's a really good explanation. However,
At least it seems.
it's not gonna be easy. It's not gonna be easy. I will try my best. Because what we're gonna do is we're gonna establish the rule and then you'll see. And we gotta do problems. It's just as simple as that to really understand this. And there's tree diagrams you can do and all that stuff, but whatever. I saw a way because some people are writing in a slow fashion. Okay, what you were drawing? Okay. All right, drawing in a slow fashion. All right, so let me zoom out. And then I just want to, let me go ahead and just make a division there. All right. Obviously, we're not there yet. We got more stuff to cover. So let's just go back to the original rule. And I can zoom in, but it'd be nice if you guys could see that, but you can't. So let's zoom here. Okay. So we had the following. The probability of A and B must equal the probability of A times the probability of B given A. Okay. Now, if the probability of B given A equals the probability of B, and this will occur, this occurs if events A and B are independent, then the probability of A and B must equal the probability of A times the probability of B. This is for independent events. Now, remember, you can rearrange this and say that the probability of B given A equals the probability of A and B divided by the probability of A. Now, another thing you could do, and remember that the probability of A and B is equal to the probability of B times the probability of A given B. That's also true. So the probability of A given B is just the probability of A and B divided by the probability of B. That's another thing. And so, in theory, we should be ready to do some problems. We'll go over them. So now, if there's more if there's more than two independent events, if it's A and B and C and so on, then this is just probability of A times the probability of B times the probability of C times dot, dot, dot till forever, until it ends. So that this occurs if the events are independent, of course. Now, here goes nothing. So I'm going to go to page 79. And I'm going to try to paste the problems right here to make my life easier. And hopefully this is going to help you do the homework assignment, because I'm really going to push this homework assignment as a grade. Not because I don't like you, but because I like you. So do you want me not to like you anymore? Okay, good. So you guys like homework. Homework is good for you. I think homework, if you do enough homework, you're granted immortality. Is that true? No. No, you never heard of that? Nobody's ever told you that? That if you do enough homework, like you're granted immortality? What happened? Your teachers don't use what? Let me tell you, if you use the surface enough, you come to appreciate it. Yes. I thought I wasted my money with this, and with Corona, this has proven its worth.
How much cheaper is the iPad?
Huh?
How much cheaper is it than the iPad?
How much of the what?
How much cheaper is it than the iPad?
No, they're about the same. The iPad, this is a little bit more expensive, but I bought it on special. This is a Surface Pro 7. I'm not sure what it is, honestly.
She wanted to get that one.
Yeah.
My back broke.
Yeah, broken class. Okay, so let's take a look at these problems together. These, of course, are the basic problems. Hopefully you could do them. It says there, two cards are drawn without replacement from an ordinary pack. Find the probabilities that both are picture cards. Now, we have to be, it says without replacement. So this is going to cause that second event to be dependent on the first event. So let's see. Let's try and answer number 2. So I'm gonna have to start it down here. Can you see this part, or you can't see it? You can see it. So let's begin with 2A. It says probability, both cards are picture cards. So we say probability of pick and pick. So here's how I would do this problem. I would actually, here's the rule. Probability of A and B must equal the probability of A times the probability of B given A has happened. So let's see. This is going to be probability of pick times the probability of pick given pick has happened. So now, what's the probability of getting a picture card on the first draw? How many picture cards do we have? 12 out of 52. I'm going to keep that card in my hand. What's the probability I'm going to get another picture card given I got a picture card in the first draw and I kept it? 11 out of 51. And you multiply them. So let's rehearse what's happened here. What's happened here, well, you can do the math on that. Who cares? What's happened here is, how many ways can I pick the first picture card? How many ways can I pick the second picture card? But how many ways could I have picked the first card? 52 ways. And how many ways could I have picked the second card? 51. The bottom represents the total number of ways I could have selected 2 cards. And the top selects the total ways I could have picked picture cards. Duh. Right? Got it? That's all we're doing. We're just doing fancy ways of counting. That's all it is. But here's the thing. That's why we have the rules. Next chapter's on counting. Okay, so don't worry. You're gonna count. Okay, neither is a picture card. So see, I'm gonna stop the recording. And now that I've armed you with an example, could you please try and do B, C, and D on your own? And I'll pause the recording. And- No. Multiply it out and reduce it. You're smart enough for that, I think. No, I know. Resume recording. All right, so how about the next one says neither is a picture card. So the probability of, so not, I'll just use squiggly line. So not pick and not pick is equal to the probability of not pick times the probability of not pick given not pick, right? So what's the probability of not picture card? All right, how many cards are not picture cards? 52 minus 12 is 40. And then what's the probability not picture given? I've already gotten a not picture one. 39 out of 51. That makes sense? Yes.
They said each one.
It's not. But does that make sense? Okay, good. All right, C says at least one is a picture card. So C says the probability of at least one is a picture card. So let's talk about what that means. What that means is either you have picture card, picture not picture card, or not picture card and picture card. Would these meet the criteria of at least one picture card? Okay, agree? Now here's the thing. What's the only remaining possibility? Not picture card, not picture card. So these four listings I have here, only these meet that criteria, correct? So in theory, the probability of at least one picture card is going to require you to take the probability of picture and picture plus the probability of picture and not picture plus a probability of not picture and picture. That's what it's going to require you to do. However, if you realize that if I would do all the probabilities of all these together, if I actually did it, since it should come out that the sum of all these probabilities equals to 1. And since I already know this guy, because I solved it here, I know that at least 1 is 1 minus the probability of none being a picture card. So that's 1 minus the probability of not picture and not picture, and it keeps you from having to do all of them. So it would literally be 1 minus not a picture card, which is what B is. Thank you. Está bien. You do that. Does that make sense? Because what happens is, now when I look at the next problem is at least one red. It's super easy. At least one red, the probability of at least one red card is equal to 1 minus the probability of none red. Well, what's the probability of none red? It means the probability of what? Of black and black. So the probability of black and black must equal the probability of black times the probability of black given black. I put G. And remember, this is without replacement. So this will be the probability of black is 26 out of 52. Half the cards are black, half the cards are red. Then you have 25 over 51. And then you just go, okay, so therefore the probability of at least one red must equal 1 minus 26 times 25 over 52 times 51, whatever that comes out to. And you're done. And this is the game we play. And this is why we memorize the rules. And this is why we practice. And this is how we learn. When we do the homework and we can't do it. But we're enthusiastic about learning. And we dream of this, right? Make sense? Good. Now, of course, you're going to have problems. I'm going to assign you homework. You can come back and we can try and do it. And then I prepare you for a test on this based on questions that have been released before. And then you're going to complain that it wasn't enough because it was so much harder, blah, blah, blah. And I'll review it. I'll curve the grade and we continue and continue. Fair enough? Okay. So I'll wait because some people are writing, even though yes.
I mean, we don't want to take it.
I want to give you guys that, but I don't waste time either. Huh?
I was saying that we don't want to, but you don't.
Not the quiz, but like just
I
like
kind of don't want
list
it
the
by surprise.
equations.
At least so that we can like have it.
Like just to have it, but not.
I should just print it out for you guys.
Yeah.
I should just print out the reference sheet to get used to it. Just go. You don't look like a criminal.
I'll blame it on you. It's really right.
No, don't blame it on me. Blame it on. Yeah, on Woods. On Woods. All right. So look at number 3. Events A, B, and C satisfy these conditions. There we go. Calculate probability of A and B, probability C given B, and probability of A given B. I'm gonna pause this, look at your notes, and see if we can do that. Let me pause. Okay, so look, let's try and do, I'll do it in orange, 3A. So 3A, the probability of, yes?
This one's like 4 for kids for 8th grade.
Today?
Yeah.
I can't say no to her. Yeah.
Okay, it's gonna be like 4 kids.
Yeah. Are they the bad kids?
I have no idea. It's just in the list.
Okay. Yeah, tell me they're bad. They're good people. Okay. Okay. Take care. So the probability of A and B must equal the probability of A times the probability of B given A, or perhaps it could also be the probability of B times the probability of A given B. So can you do that? Did they give you the probability of A? Did they give you the probability of B given A? So all you do this question is, oh, the probability of A is 0.6. The probability of B given A is 0.45. And you do what? You multiply them, correct? Was that hard? No, it was not. How about B? Right? 3B. It says the probability of C given B. Well, what's the probability of C given B? Well, it must be equal to the probability of C and B divided by the probability of B. Do they give you C and B? No, but they give you B and C. And by the way, B and C is equal to C and B. It's commutative. That's allowed. So they give you 0.28. Probability of B is 0.8. And you divide it. Now C, 3C, they're asking for the probability of A given B. Well, that has to equal the probability of A and B divided by the probability of B. The probability of A and B was determined in part 3A, 0.6 times 0.45. The probability of B was given to you, and you just carry out that math. Yeah, I could potentially move it. Yes, why not? And that's how you do those drawings. That makes sense? Was that hard? Okay, so I don't think I'm gonna be able to do number 4, but I can give it to you for homework. No, you gotta do homework. Come on.
You should show us like stuff how to do.
No, no, no.
Yeah, yeah. You should record it too.
No.
This has
Well, this has, yes, this is, yes, yes. It's been recorded. You have the notes. How are you? I haven't seen you forever. What's up? Oh my gosh, did you lose weight or gain weight? Go. Bye, Mom. All right, guys, let me go ahead and stop this recording. And let me go ahead and update it onto this.